In the very first lesson, we talked about the idea of moving from an average rate of change to an instantaneous rate of change, or the change at a particular point instead of over an interval. But we haven't had an occasion to apply that yet. So in this video, I want to talk about that with a real-world example. So this problem says a ball is dropped from a height of 64 feet. Its height above the ground in feet, t seconds later, is given by s of t equals negative 16 t squared plus 64. And so this problem asks us to find the instantaneous velocity of the ball when it hits the ground, and also to find the average velocity during its fall. I actually want to look at problem B first. So B asks us to find the average velocity during the fall. And in other words, they're asking us to find the average rate of change or the slope of the secant line during the fall. So we're actually finding the slope of the line segment right here. And so to find the slope of that line segment, we can go back to our algebra days. So we have to give those values or those points some coordinate pairs. So this first point, this is 0, and it corresponds to a y value of 63, or an s value in this case. So this is the point 0, 63, and the second coordinate pair is going to be 2, 0. And to find the average velocity, that's equal to the slope of that line. And we can do that using the formula y2 minus y1 over x2 minus x1. So we get 0 minus 63 over 2 minus 0. And so that is negative 63 over 2, which is equal to negative 31.5. And we're talking about a velocity, so it's going to be feet per second. Let's look now at problem A. Problem A asks us to find the instantaneous velocity of the ball when it hits the ground. So remember, when we're looking for the instantaneous velocity or instantaneous rate of change, we need to take the derivative. And our position function is given by negative 16 t squared plus 64. And if we find the rate of change of position, that is the velocity, right? So the velocity is equal to the derivative of the position function. And that is going to be the derivative with respect to t in this case of negative 16 t squared plus 64. And if you need to, you can use your derivative rules. So you could use the sum and the constant multiple rule, and what you'll end up with is negative 32t. So the velocity function is given by negative 32t. And notice that it changes depending on what our t value is. So we are finding the velocity at a particular point in time, and they want us to find it when it hits the ground. And so when it hits the ground is at 2 seconds. We know the position is 0 at 2 seconds. So we can take the velocity at 2 seconds, and we get negative 32 times 2, which is equal to negative 64 feet per second. Now you may be wondering why the velocity at a particular point could be so different from the average velocity over the interval. But actually, if you look at the picture, this makes sense. So the average velocity is the slope of this line segment, and we found that to be negative 31.5. And if you look at the slope of the tangent line to the curve at 2, you actually get something that is about twice as steep in the negative direction, right? So it makes sense that the velocity at 2 would be about twice as big as the velocity over the interval.